All right, so last chapter for today, okay? So there's not going to be new methodology anymore or new models because we've just finished that. But this chapter has been included in the course because we have for many years received questions about how do you now do sample size calculations and power analysis in this context. And the first thing you need to realize is that that's not an easy question, because the moment you say sample size, then you have to know what that really means, because the size of your sample is a combination of the number of subjects and the number of measurements per subject. And you can play around with that. So in many situations, you wonder whether you should take more subjects and maybe fewer observations, or whether you should take less subjects and more observations per subject. And there's no easy answer to that, and it really depends on what you're interested in. What is it that you want to test? What is your hypothesis of primary interest that you would like to test? That's one thing. The other thing is that what you will see here is how you can do the analysis, because there's many software packages out there that do power analysis or sample size calculations, but it's rarely the case that they would help you in doing a power analysis if you have longitudinal data, or in the context of mixed models. And then you're just on your own and you have to program things, but it happens to be that you can do these analyses in SAS. You need to use a trick, however. So you need to trick SAS to do the calculations for you, and that's kind of strange, because if you do a power analysis, you don't have any data. So how will you then use a statistical software package to do that? And we can do it in proc mixed. And the way we will do it is we will set up an artificial data set and then feed it into proc mixed in order to calculate the power of a particular design with a number of subjects and a number of measurements at particular time points. So how does it work? And then, so I'll just explain you how it works in what the methodology is, how you do it in SAS, and then we will go through a number of examples just to give you some feeling of what designs are now powerful and what designs are not powerful, so that you get some intuition behind that. Okay, the situation is the linear hypothesis that we discussed yesterday, a general null hypothesis of the form L times beta is equal to 0, versus the alternative that L times beta is not equal to 0. And most hypotheses in practice can be formulated in this general framework. And then we've seen yesterday that the F statistic that you use for that is this one. That's our F statistic. Okay, so basically it's the estimate of that linear combination here, with then here in the middle the covariance matrix inverted, and then you have that estimate again, but then transposed, and that makes it like a quadratic form, which follows a chi-square distribution if you do a Wald test, or it follows an F distribution if you do one of these tests where you take into account the uncertainty in the estimation of the alpha parameters. So the approximate null distribution of that test statistic is an F distribution with the numerator degrees of freedom equal to the rank of L. We've discussed that yesterday. And the denominator degrees of freedom are then calculated using any of these methods: containment method, Satterthwaite approximation, Canard-Roger approximation. We had that discussion yesterday. Now, if you want to do power analysis, you need to calculate the probability of rejecting your null hypothesis under the alternative hypothesis. That's by definition the power of your test. So it means that you need, for your test statistic, the distribution under the alternative. And that's not going to be that F distribution that we have just discussed here, because that's the null distribution. Now, it turns out, and people have done extensive simulations to get to this, it turns out that the distribution of your test statistic under the alternative hypothesis, where you have L beta as true value, let's say, for your linear combination of parameter values, that distribution for that test statistic can still be well approximated by an F distribution with the same degrees of freedom as under the null hypothesis, but then it's going to be a non-central F distribution with non-centrality parameter given here. Now, that's something you also encounter if you do a power analysis for just a simple t-test. What you need is the non-central t distribution. Or if in linear regression you would do a power analysis, you need a non-central F distribution. So here the same holds, and you see that if you look at this expression and you would look at this value under the null hypothesis, then L times beta becomes 0, and then you're back in the central F distribution. So this is a more general result than what we discussed yesterday. Here the result is that this F statistic from the previous page follows approximately an F distribution with degrees of freedom equal to the rank of L for the numerator, and then the denominator degrees of freedom needs to be approximated using any of these methods, and then with this non-centrality parameter. Well, that's basically all you need to do your power analysis. If you know the distribution under the alternative, you can do your power analysis. The only problem is that in a practical situation, you need to calculate this. Well, you can do that by hand, but it's not going to be easy. And what you do see is that it depends on, of course, the true values for beta, but it also contains your covariance matrix. And of course, we're not surprised by that, because also in a univariate setting where you have a two-sample t-test, we know that the power of your test not only depends on the true difference between your two groups, but it also depends on the variability in your two groups. So that somewhere that variability needs to come in, that's something you can expect. So here, that variability is represented by that whole covariance matrix. So calculation of this non-centrality parameter is not such an easy thing to do, because you would have to program it, and you would need a programming language which allows you to work with matrices. But there's programs out there, so you can do that, but there's a simpler way to do it, and that is to have SAS do that calculation for you. And how we do that is by noticing that this non-centrality parameter here that you see is actually the same almost as this expression in our F statistic. The only difference is that denominator, which is not there, but we know what the rank L is, that's very easy. And what is also different is that in our F statistic, I get here beta hat, while I would need it for beta, the true value, under the alternative hypothesis. So what will the trick be? The trick will be to set up a data set, an artificial data set with artificial responses, but with the same design as the study that we have in mind and that we would want to do in the future. So many subjects, so many repeated measurements per subject. So I'm going to set up that data set. I'm going to try to figure out what responses the subjects should have, such that if I fit that model, that the F statistic that comes out for that hypothesis is this value here. So that's what I'll do. So I'll try to construct a data set such that if I fit my model, my estimates for the fixed effects or the values that I want to pre-specify. So I'm going to pre-specify beta, because that's what you do. You pre-specify in a power analysis what should be the effects that you want to detect, the smallest effect that you want to detect with your future study. So you know your beta, you have it in mind, and now I'm going to construct a data set that if I fit my model, the estimate for the fixed effects is exactly the value that I wanted. So how will I do that? So, well, apart from that, what you then still need to do is, once you have your F statistic, you multiply it by the rank of L, and you would have your non-centrality parameter. So how will we do that? Well, we will set up a data set of the same dimension as the experiment we have in mind. So you have to picture it. Suppose that you want to calculate what is the power of an experiment if I would have, let's say, 100 subjects, 5 repeated measurements each, and I would take them at those particular time points. What is the power? And I can do that for one design, and then afterwards I can do it for a second design, and I can do it for a third design. I compare different designs on the basis of their power, and then I just choose the design which has the most power. That's what you do. And if you do it with 100 subjects and you see that the power is only 60% and you wanted 80, just repeat it and then just take some more subjects in your data set and play around until you get a power that is acceptable for you. So that's how we will do it. So we will play around with designs to get a study that is acceptable in terms of power and that is practically feasible, because also you have practical considerations that you have to take into account. Sometimes there's not more than so many subjects you can use in your study, or there's not more than so many observations per subject you can have, but then you can start playing with the time points at which you take your measurements, because that's another issue. You can say, I want 5 measurements per subject. Where should you take them? Equally spaced, or should you take 2 at the beginning, 2 at the end, and 1 in the middle? You can play with that. And depending on the model you have in mind, you can, or the setup, you can play with that, play a little bit with these time points, and each time you calculate what is the power of this particular design, and then you choose the design that gives you the most power. Yes? Yes, but in a designed experiment, there are no covariates. In a designed experiment, what it usually is that you have like a number of groups you want to compare, 2 different groups, let's say, and you have to set up your study, and you want to decide at which time points do I need to take my measurements. And yes, you can have in mind to correct for additional, let's say, covariates such as age or whatever, but then what you do is you just do your power analysis without the correction, and then you know that if you would add additional covariates, which would be important, the impact will be that you will reduce the variability which is unexplained, and your power would be even larger. So you then do a power analysis in a context where you assume there's no covariates, and if you then afterwards can include some covariates, then you will even gain power. You will be even more efficient than you had hoped for. Okay, yes. That depends. If that covariate is really explaining a lot of variability, that's not the case. And if it's not explaining much variability, then it's not worthwhile taking into your model. Right? I mean, the gain by putting in an additional covariate in a model is somewhere finding a balance between how much variability is explained and how much additional uncertainty is there due to the estimation of that additional parameter. So if there's much more variability explained, then that will dominate. And yes, there's a little bit additional uncertainty in the estimation, but what you will gain is really dominant compared to what you lose by estimating an additional parameter. And again, this is an issue that is beyond just longitudinal data. If you say, I want to set up a study to compare two different treatments, and I'm only going to take one measurement, purely cross-sectional, so you treat your patients, and after so much time you will just take your outcome measure, and then you would think of a t-test. Also there, you could say, well, maybe I want to correct for age. Well, also there, you would have to either take that into account in your power analysis, and that would make it much more complex, because then you have to pre-specify in advance what all the ages would be, which is not realistic. So what people do is they do a power analysis without age, and then they hope that afterwards age will explain sufficient variability so that you would gain if you bring it into the model. All right. So let's do that. So how will I now make sure that the data set that I set up is such that if I fit my model to that data set, the fixed effects that are estimated are exactly the values that I had in mind? Well, what you need to do is you use as responses just the average values that you want to obtain. And that's the right choice. Why? Because my fixed effects estimates, as you know, will then be given by this expression. Since I used as my y's xi beta, then this part will vanish with this part, and the only thing that is left is beta. So I can make sure that what comes out as estimate is the value that I have in mind, by just using these responses in my artificial data set. And you will see how it works in practice in an example. So if I construct that data set, I put it in proc mixed, I fit my model in proc mixed, and I ask for the F statistic for that particular hypothesis I'm interested in. I know that this F statistic, apart from the rank L in the denominator, will be the non-centrality parameter I was looking for. And that's all I need to do the calculations. And then I can calculate my probability to reject the null hypothesis if the alternative hypothesis would be true using the non-central F distribution. So, how will we do that? We will calculate that F value. That F value will give me my non-centrality parameter. Then I'm going to use proc mixed to calculate that non-centrality parameters as well as the degrees of freedom, because that's the other issue. You've seen yesterday that these degrees of freedom sometimes are not even integers. So, and these calculations like Cantor-Droger or Satterthwaite are not easy calculations. So it's very convenient that you have a software package who does that for you. So what comes out is the following. You have SAS calculate for you that non-centrality parameter in proc mixed, and then you will first calculate the critical value. So what you need is your central F distribution. So the blue one is your F distribution that you would have under the null hypothesis. You will calculate the critical value. So here it's denoted by F critical, FC. And that's defined as the value such that right to that value you have alpha probability, your significance level. And now you want to know what is the probability if the alternative hypothesis would be true, that I would reject my null hypothesis. So I need to look under the alternative hypothesis, so under the alternative distribution, which is the non-central F, and I need to calculate what is the probability that I would have a test statistic to the right of the critical value, and that's the power. And these calculations I can also do within SAS. SAS can do that for us. And you can do that with the functions F inverse, so that's to calculate the critical value. So you specify your tail probability, and F inverse gives you the critical value. And then with the function prop F, under a non-central F distribution, you calculate the probability to the right of that critical value. So that's how you would do it. So let's just do it immediately in an example, just to show you how it works. And I reconsider my example with the rats. Actually, that's an example that we really had truly in the consulting, because you have to imagine with the rat data, that was done here in dentistry. We were not involved in the design, so it was too late to do that, as always. And what happened is we did the analysis of the data that you've seen, and you've also seen earlier today when we talked about information criteria that there's no significant difference between the groups. And then immediately the question came from the clinicians, well, isn't that a problem of the missingness? Because we lose so many rats during our study who die because of the anesthesia, so we lose power. Isn't that the reason why we don't find any differences anymore? Could be. And the next question, of course, was if we would do the experiment next time, how would we have to set up the experiment? Because you know that each time you take a measurement, and you can calculate that probability, there's about, as far as I remember, 11 up to 12% chance that the animal dies. So you know that the more measurements you will schedule, the more likely it is that the animal will not make it until the end. You've also seen, for that data set, that the correlation was pretty high. We've calculated it today. The correlation was 0.71. So there you can see, or you can guess intuitively, that it's probably not very useful to schedule 7 measurements per animal, because that 7th measurement will not going to give you a lot of information anymore if you already have 6, and since they're so highly correlated, and by adding additional measurements, you run the risk that the animal dies, so that you lose it. So there's going to be the need for some, again, you need to find a balance between taking more measurements and then running the risk that you lose the animal, and maybe having a few less observations, but still have enough power to do your test. So that's why we started thinking about how should we design longitudinal studies in the future. Now, the example I just gave is, of course, more complex, because you can, with these rats, you can come up with a design and say, I would do it this way, but you know that's never going to be possible to realize because they will die. No matter what you do, some will die. So it's more complex than that. In a full design, you should take into account the probabilities of dropping out. We're not going to do that here, okay? But if we look at our rat example, and we now would want to know how many rats would we need, so assuming that you can do the full study without any animals dying, how many rats do I need? to get a reasonable power, let's say. Well, we can do that. So this is the model, the random intercepts model. This is how you would fit that in proc mixed. I need a contrast to test equality of my slopes, because that's the test of interest. Here is where I will calculate my F statistic. And the new experiment assume that you would design a new experiment to test this hypothesis if the true differences between the groups are given as specified here in that table. So the intercept, we take value 68. Now that's not very relevant. If you want to compare slopes, that intercept, you need to plug in a value, but whether you put 68 or 70 or 0, that's not going to change your power. Okay? And then the same for the slopes. Here it was specified in the control group a slope of 6.5, in the low dose group 7, in the high dose group 7.5, but the only thing which is really important is the relative difference. That's the same in a t-test. In a t-test, all you need for the power analysis is the distance between your groups, not the actual values. But here we have to plug in some value, okay? And then we, of course, need some covariance parameters here to specify, like in a t-test, we need to specify the variability in my groups. Well, here the parameters is the random intercept variance and the residual variance, and here we just use values similar to what happens in the previous experiment. 3.6, 1.4. And these were the values that then lead to that correlation of about 0.7. So how would I do that? Suppose that I want to calculate the power of a design with 10 rats per treatment group. How would I have to set up my artificial data sets? Well, I create a new data set. So here you need some data steps, and I call it data power. I need 3 treatment groups. So treatment goes from 1 to 3 in steps of 1. The rats go from 1 to 10 in each group. The ages go from 50 to 110 in steps of 10. And this is where you can play with your design. You can put in more rats, fewer rats, more time points, less time points, other time points. That's where you can play around with your design. But here, let's just do it similar to what was done in the past, and let's calculate the power. Of course, in my model, I don't need age, but I need that logarithmic transformation of age. So I need to calculate it here. So t is the logarithm of 1 plus h minus 45 divided by 10. That's the transformation that we used for the rat data. And then I need to define my responses. So up to here, my design matrix has been specified. The time points at which measurements are taken, how many subjects, how many groups, and things like that. Well, now I need to specify my outcome, and my outcome is the predicted mean that I want. So if treatment is equal to 1, then the outcome is my intercept plus the slope in that group multiplied by t. If the treatment is group 2, then it's the intercept plus the slope in group 2 multiplied by t. If the treatment is 3, then it's the intercept plus the slope in group 3 multiplied by t. So here I construct my artificial data set. So here it means at the end of this step, so you save it here, you end all these do loops. At the end of this data set, I will have 3 groups of 10 rats each, and the response profile for all the rats in the group is the same. They all have exactly the same outcomes. Okay? But I know if I now fit my model to this data set, that what comes out as fixed effects are this intercept and these slopes. And that's what I needed. Because all I'm doing is I'm using proc mixed to calculate that F statistic for me. That's the only thing I use ProcMixed for. So now I'm going to fit my model to my data set. So the data set I'm specifying is power. The program you see here is exactly the same as the program you've seen 2 pages ago when I showed you how you would fit that model to a real data set. There's only some small changes, and one is that I need to specify what are the variance components. I have to pre-specify them. Otherwise, SAS would start estimating them. Well, the variance components are 3.6 and 1.4, and you can specify them in SAS by using a params statement. So in the params statement, you basically specify starting values for the covariance parameters. But of course, I don't want them to be starting values. I want to keep them fixed. Well, I can do that by adding here no iter and no profile. So especially the no iter, you can guess what it means. It means no iterations. Don't iterate to estimate these parameters. Just keep the parameter values fixed to the values that we have specified here. And there's one additional statement, which is again an output delivery system statement, where I want to save the results from that contrast statement here, such that I can start calculating with that F statistic, because I have to calculate here the critical value and then the power afterwards. So I want to save that, otherwise I would have to do the calculations by hand. Don't want to do that, if possible. Yes? Yeah, well, you need the combination of the two. It's a technical issue in SAS. You need the combination of these two to make sure that SAS will not do any iterations, not just for your variance components, but also not for the fixed effects. Because otherwise, what SAS is doing, it's like using the likelihood function, the Lemmel likelihood function that we've seen there, and it would start maximizing it with respect to beta and alpha simultaneously. So here you specify that it's not doing any iterations for the alpha, but you also need to specify that it's not doing any iterations, not even for the betas. But if you, how would I explain that? It's a technical issue. It has to do with how SAS is. We cannot. It's impossible to really explain what happens without going into the details of how SAS has programmed it. I mean, you're perfectly right that, strictly speaking, it should be sufficient to just write here no iteration and then let the procedure go. And then you should get the right results. But internally, how SAS is doing it requires you to put here a no profile option. And that's all I right now I can say about it, because otherwise you would have to go into... Beta will be estimated, yes. But of course, there's no variability in these profiles, so you don't need an iteration. And the first step in the whole iteration process is already sufficient to immediately get you the right results. So it's not a full iteration process that you would have as you would have in other contexts, because all the animals in a specific group have exactly the same profiles. So there's no variability there in that data set. It's a completely artificial, constructed data set. All right, so we've discussed this. So then, what I'll do is, in this output data set, we save the results from the contrast statements in an output data set C, and now we're ready to do our calculation. So what I'll do is I'll take that C data set, that I will write it down in a new data set power. You can call it anything. I specify my alpha level that we need, so the 5% level of significance. Then we calculate the non-centrality parameter. And what is the non-centrality parameter? If it's the F statistic, and in your output data set, that's in the variable with the name F value, multiplied by the numerator degrees of freedom, and in your output data set, that was the variable with the name num_df, numerator degrees of freedom. So that's going to be my non-centrality parameter. And then I use that F inverse function, and the F inverse function calculates the value here on your x-axis for an F distribution with non-centrality parameter 0, because we're working under the null hypothesis, with degrees of freedom num_df and denominator df, which are also in the output dataset, because SAS calculated that for us. And then with probability to the left, 1 minus alpha. So SAS wants you to specify the probability to the left. So if you want alpha to the right, you need to specify 1 minus alpha, which is the probability to the left. So what comes out is my critical value. And then I can calculate the power. And my power is 1 minus the power is the probability to the right of my critical value, but what SAS is calculating is the probability to the left again. So my power is 1 minus the function prop f, so where the prop f is calculated to the left of the critical value, again with the same degrees of freedom, and now I need to use my non-centrality parameter. That was calculated before. And that's going to be my power, and then all you do is you print out your results. And this is what you get out if you print out that small data set. So you see here, this here is the output from the contrast statement in proc mixed. This first part up to prop f. And then I added alpha here. I added my non-centrality parameter. I added my critical value, and I calculated my power. And then you see that for a data set with time points as we had here in this particular situation, so 50, 60, 70, up to 110, if you would have 10 animals per group, and all these animals would stay in the study until the end, you would have 78% power to detect the differences as we have pre-specified them. If you think that's not enough, you can just increase the group size. You just run that whole program again, and you just repeat here, where is it? Rat 1 to 11, 1 to 12, 1 to 13, and you increase the number of animals per group, and then you would get the powers 82%, 85%, 88%. With 20 animals per group, you have about 98% power. Yes? Yeah, yeah. That's exactly how you do it. But the problem is that if you have missingness, your power becomes a random function. Random because of the missingness mechanism, which is random. So if you would do that, like what you suggest, and you do it once, you have a power. You do it the second time, you get another power. So you would have to do it hundreds of or thousands of times to get an idea of what is now the distribution of the power for a particular design. And then you can repeat that for another design. And then this way you can see what is now the safest design to choose. But that's exactly what was done. And that's been published also. So you look at the distribution for the power under a particular missing data mechanism. And you can build in many mechanisms. One would be that the probability to drop out just is constant. Each time you take a measurement, it's 12% probability. But with patients, you could think of a situation where the probability to drop out would depend on how many measurements they already had. Patients get tired of coming back to the hospital, let's say, and the longer they stay in the study, the more likely they are to drop out. Well, you can put that in. So you can easily extend that same principle here, but then you need simulations. Now, just to get a little bit of feeling what that power depends on, let's play around, and we will repeat this for different values for the variance components. Because you have to put in these variance components. And we know from a two-sample t-test that the variance within your groups is important if you want to calculate your power or your sample size. So we expect the same thing to happen here. Only here we have two variances, the random intercept variance and the random slope, and the residual variance, sorry. So how crucial are they? How do they affect the power of a particular design? Well, let's just try it out. So what you see here is, again, for the situation, 10 rats per group, so the previous situation, but then for different values for these two variance components. So for D11, before we had 3.6, and for sigma squared, before we had 1.4. And now I just changed that a little bit. So we have 9 different scenarios. And then what you see is the following. If you just look at, for example, a fixed value for D11, then as the variability in the residuals increases, the power decreases. That makes sense. Because if D11 is fixed, and the sigma squared increases, you just have more variability in your data. And more variability always, well, usually means less power. If you keep sigma squared fixed and you let D11 increase, then you have something, then what you see is that the power here decreases. What you also see is that if you look at the diagonal, then the total variability stays the same. Because the total variability is then each time 5. Then you see that the better situation is with a lot of between subject variability and little within subject variability in terms of power. You will have more power in this situation than in that situation. So what it means is that the power decreases as the total variance increases in general, but what you see is that if you keep the total variance constant, then the power increases if the intra-class correlation increases. So the correlation is a good thing for you. The more correlation, the better. Of course, there's nothing you can do about that. There's a lot of correlation, or there's very little correlation in the type of outcomes you're studying. You cannot influence that. But it's just to see what happens if there's a lot of correlation or if there's very little correlation. So the more correlation here, the better. Let's take a look at another example. It's not always like that, as you will now see. here is an experiment which is not longitudinal, but we still can use mixed models for the analysis. Suppose you would have an experiment where you want to compare two different treatments. We call them A and B. And you would have N, capital letter N, general practitioners, so doctors, who would treat their patients. And each doctor would treat small letter n subjects. That happens all the time, okay? Let Yij be the response for subject J treated by Dr. I. So you see, that's repeated measurements. Again, it's not longitudinal, but it's repeated measurements. Then the analysis definitely should account for the variability between the doctors. So how can we do that? Well, we can build a model, a linear model, and it's going to be a linear mixed model, where you say I have an average effect for the treatment A, an average effect beta 2 for treatment B, but then I have a doctor effect, which is actually a random intercept. Different doctors can have different levels in their outcomes. So B1I represents variability between the doctors. And then you have errors, because within a doctor there's still some variability between your patients. So it's exactly the same type of model as we've used before. It's clustered data, it's repeated measurements, it's mixed models, but it's not longitudinal. So there's no time dimension here. And let's assume as true parameter values for A, the average is 1, for B, the average is 2. Again, the actual values are not important. It's only the distance between the two which is important. So I could equally well say 11 and 12. That would give me the same results in terms of power. And for the variance components, well, if this is a new study, you often don't know what to do. What you sometimes can do is look in the literature where people have studied similar problems, and you would see in the literature if they present tables with descriptive statistics, you would see often like an estimate for the standard deviation in your outcome, and based on that standard deviation that I've seen in some paper, let's say, I can guess, well, I know that my variability is about 4. But that's the total variability. How to split that up in variability between doctors and within doctors, that's not reported, of course. That's not what people usually do. So what I'll do is, and that's just for the illustration here, to get some feeling about when do we have a lot of power and when do we not have a lot of power, what I'll do is I'll just use a number of scenarios to calculate powers, playing around with D11 and sigma squared, but make sure that the sum is about 4. So the individual variance components are not known, only the total variability is known to be about 4, let's say, and I will now do some power analysis to, for several values of the intra-class correlation, and that basically means splitting up in D11 and sigma squared. But make sure that the sum is equal to 4. So I'm going to use different values of D11, and then, of course, sigma squared immediately follows from that. And now I'm going to look at two different cases. There's two different ways people often do experiments in this context. The first one is that treatments are assigned not to patients, but to doctors. So what it means is that you randomly subdivide your doctors in two groups, group A and group B, and then if in that context, all the patients treated by the same doctor would get the same treatment. So Dr. 1, for example, would always use treatment A. Dr. 4 would always use treatment B. That's what is called a cluster randomized study. You randomize the clusters rather than the patients. That's done a lot in practice. So let's take a look at powers. what you see here, I use the methodology we just discussed to, to calculate the power for a design where we have 50 doctors, 2 times 25, and each doctor would treat 10 patients. So in total, we have 500 patients in the study. And here you see the powers for different correlations. And what you see is that as the correlation gets larger, the power gets smaller. So it's the opposite of what we had before. And that's why I said before, it's not always that correlation is good for us in terms of power. There are situations like here where the correlation is bad for it. You would hope that there's not much correlation in a study like that, meaning that there's little variability between the doctors. If the doctors are too different, then you're in trouble in a design like that. If there's very small differences between the doctors, then you're fine. That's what it basically means. It's not time. Wait and we will see why it is. Because in the next case, we still will not have time, but the experiment will be different. In the next case, the treatments will be assigned to the subjects, to the patients. So each patient would be randomized, and a doctor would treat half of his or her patients by treatment A and half by treatment B. And now let's calculate the power for 2 times 5 subjects, so still 10 subjects per doctor, 5 treatment A, 5 treatment B, and with 10 doctors. And here you see the powers, again for the same scenarios. And there's 2 things that you immediately see. First, if the correlation increases, the power increases as well. But more importantly is that these powers are way larger with many less subjects. I have here in this scenario only 100 patients. And before I had 500 patients. So you see that there's many different things that can happen in situations like that. Why is that now? Well, the key difference between these 2 scenarios and why it is that here the correlation is good for us, in the previous scenario the correlation is not good for us, is the fact that the effects that we're estimating and testing is, in this case, a within cluster effect. It's within the doctors. In the previous case, it was between the doctors, between the clusters. Because half of the doctors got treatment A, the other half got treatment B. So if you want to compare treatment A with B, it's between the clusters that you're doing a test. While here, it's within the doctors you're doing a test. And then the correlation is good for you. The more correlation, the better, because a lot of correlation means a lot of between-doctor variability. Now, think of what we did on Wednesday when we talked about the pair t-test. What is a pair t-test doing? It's calculating differences within subjects, and this way, you get rid of all the variability between the subjects. And that's where you gain your efficiency. There's a source of variability that completely disappears by taking these differences within clusters. And the same happens here. By looking at internally, what happens is you look at differences within doctors to estimate your treatment effect. And by doing that, you can avoid all the correlation between the doctors. So, what is the conclusion? the conclusion is that you have to be a little bit careful and that you cannot just say in general correlation is good or correlation is bad. It depends on the design of your study, it depends on what you're interested in. But if you're looking, like for the rat data, if you're looking at the slopes and you want to compare slopes, slopes are things that have to do with changes within subjects. If you want to say something about slopes, correlation will be good. We've seen that. Okay? The same with these doctors here. Correlation is good if you're looking at effects within subjects. But if you're looking at between subjects, effects, then correlation is a bad thing. Then you can only hope for as small correlation as possible. And in any case, what you see, so here you see within subject correlation increases power for inferences within subjects, but decreases power for inferences on between subject effects. So it really depends on the design, whether the effect you're estimating is between or within, and on your research question, of course. But it basically means that if you're, in whatever context you work, if you can avoid cluster randomized studies, please do so, because otherwise you will need many more subjects in order to be able to tell something. So if you have you have to set up a study with this kind of hierarchical nature, like if you would have, let's say, different cities, and you go to all these cities, and then in each city you will question the number of habitants, or you would treat habitants, then it's better not to treat half of your cities in method A and then the other half with method B, but to do the randomization within the cities. Like here with the doctors, better to randomize within the doctors, because then you really gain a lot of efficiency. Mm-hmm. That's the second example, yeah. I mean, the other thing is not wrong, but you have to realize that it's, not as efficient. And of course, there's situations where you have no choice. For those amongst you who took the course last year, there was this diabetes example, which happened here in Leuven. So those who don't know the example, what happens is all the general practitioners around Leuven were asked to participate in a big study where they would get help in treating diabetes patients. And there were like two treatments. One treatment is just nothing special. That was like a control group, let's say. The other treatment is that the doctor can ask help from very specialized people in the context of diabetes patients. Now, in a context like that, it doesn't make any sense to randomly assign your patients, because you try to evaluate the doctors, and you want to know whether it's helpful to give additional support to these doctors. And of course, if you give additional support to a doctor, you cannot ask that doctor not to use that knowledge if he treats half of his patients. So there are situations where you don't have a choice, and that you automatically have a cluster randomized study. But the price to pay is that you will need many more. But there are situations where it's just impossible to do anything else. Yes. Ah, a lot. I mean, the general conclusion does not depend on the values you put in. You still will have, but the power itself will very much depend on these values. So, and that's the other thing. For many years, statisticians have been telling clinicians that they should come and talk to them before they do the experiment. Now, not all of them, because there's always people who don't want to listen, but more and more people do that. And we get questions, people coming in and say, well, I want to do like a longitudinal study. Can you do a power analysis? Now, you can do it now. Technically, we can do it. But the questions you have to ask them, like your treatment effects, what do you expect as slope in one group, slope in the other group? Maybe they have some idea. Because if not, it would mean that they've not carefully thought about the objectives of their study. Okay? So maybe they have an idea. But if you then would ask them, what model do you have in mind? Is it the random intercepts model or random intercepts and slopes? Would you need serial correlation? If so, what type of serial correlation? And then what parameter values, like the random intercept variance, how large would it be? The random slope variance, how large would it be? The covariance between intercepts and slopes, what value should I use? I mean, they have no clue. And you cannot expect these people to do that. So, and yes, if you play around with these values, you get different powers. So, the only thing you can do is say, I'm going to put in some values which are, you can ask for some data maybe from previous experiments, do an analysis to get some idea of what model would be needed, use these parameter values, and then play around with different designs where you say, now I'm going to put my time points at different places, or I would take more observations or less observations. And this way you can compare designs and you can choose for a design which is better than another design. But don't hope that with the design that you've selected, that the power that will be realized afterwards will be exactly the power that you calculated, because that's not going to happen. But what you can do is use that type of methodology to get some feeling about which designs would have more power than what other designs. And this way you can prevent people from doing experiments which are not the best way to do their experiments, but you cannot in advance say your power will be 85%. That's just hopeless, because it just depends too much on the parameter values you put in, and it's unrealistic to have a good idea of these values. But yes, you can say, well, with this kind of question, with these practical restrictions you have, it's probably better not to take so many observations, or to put your observations more at the beginning or more at the end, or to spread them all out. That's things you can do. There you can help them to choose a type of design which is a good choice for their case. But you cannot say, if you now do it this way, your sample will definitely be large enough. So what you then do is you just, you really simplify the problem, and you say, well, let's just do a power analysis. If you really want to make sure that your sample is large enough to have sufficient power, just do a power analysis for example, an endpoint analysis. And if you have sufficient observations for that endpoint analysis, you will have definitely sufficient observations if you take into account all the observations that you have. But that's the disappointing thing, that now that people come to you to ask you how large the sample should be, it's very difficult to answer that question in a context like that. All right. Are there any further questions? You're quiet. Okay, well, if not, I think I promised you to stop early, so I'll keep that promise. And I think we can stop here for today and for block 1. So remember, for the students, there's the option to have like questions. I think it's on November 8th or something. It's 2 weeks from now. And then we can further discuss issues if there would be any issues. Okay? Well, thank you and have a nice weekend. Ja, het enige is dat je gaat moeten zien dat je in je data natuurlijk de verschillende aspecten hebt die aan bod komen. Dus iets continu, iets discreet en dan ja, dat je missing data hebt liefst. Nee, je hebt natuurlijk liever in je eigen data dat je geen missing data hebt, maar hier voor dat vak is dat wel nodig. Natuurlijk, als je het alleen doet, ga je nog meer werk hebben. Hè. Anderzijds, ja, ik weet wel hoe het is dat je contact hebt met die andere studenten. Als je niet in de Leuven komt, ja, dan wordt het moeilijker om het in groep te doen. Dus je moet dat ja. Als je het toch nodig hebt, ja, dan is het ineens meegenomen. Geen probleem. Ja.
Ik heb nog één dingetje. Ik heb altijd met Lien gewerkt.
Ja.
Ja, vorig jaar heb ik ook in met Lien gedaan. Ik heb nu zo het gevoel dat ze voor die exploratieve data-analyse, dat eigenlijk dat SOS wil makkelijker zou zijn. Ik heb hier niet dat ik daar toegang heb als student zijn.
Ja, ik denk dat wel. Maar je zou eens moeten aan Carbone, van het masterprogramma, hè, de coördinator van het masterprogramma. Ik denk dat zij u gewoon toegang kan geven tot SAS. Ik weet niet hoe dat precies is, of een keer vragen aan hun, want de studenten die hebben dat al.
Ja,
dus, maar hoe dat precies loopt, maar ik weet dat er voor de studenten